To understand the basic physics of climate change, one has to think about the Earth's radiation budget. Now, we measure the Earth's radiation budget in units of energy per unit time per unit area. The reason for this is that we think about how much incoming radiation energy there is per unit time, so that would be a unit like a watt, per square meter, which then tells us how much energy is received per square meter of the Earth's surface. Now, the Earth's surface temperature in general is controlled by the solar radiation the Earth receives from the sun. There is a small amount of geothermal energy that the Earth receives from the internal heat of the Earth. That flux is something like 1/10 of a watt per meter squared on average. That's really tiny compared to the solar radiation, which is several hundred watts per meter squared. At a very superficial level, we can think of the incoming solar radiation being mostly in the visible spectrum, which is short wavelength. That is the visible light we see, also a little bit of ultraviolet light. And that penetrates the Earth's atmosphere, and some of it is reflected by white clouds, some of it is reflected by white things on the surface, like deserts or like ice sheets, and that light then would be reflected back to space. But whenever the visible light actually hits something darker on the Earth's surface, that material absorbs the energy and heats up a little bit in response to the energy flux that it receives from that solar radiation. As you know, when you go outside on a sunny day, you feel the warmth in response to your body encountering the solar radiation from the shortwave radiation, and you absorb that energy and turn it into heat. Well, heat itself is a form of radiation, but at a longer wavelength. And so we emit that heat back to the atmosphere. So when the surface of the Earth absorbs the visible light that it receives from the sun, the temperature increases and radiation is radiated back out towards space, so that essentially there's an exchange of shortwave for long-wave radiation. Over a relatively short timescale, there's an energy balance, so that the amount of incoming energy from the sun is balanced by the amount of outgoing energy, which is a combination of both the sunlight that's reflected directly back to space and the long-wave radiation that comes from the interaction with the Earth's atmosphere and the surface, and it's heating up and radiating long-wave radiation. And so you can actually match up the incoming shortwave radiation with the outgoing shortwave plus long-wave radiation. In this context, one can think about the role of greenhouse gases as increasing the surface boundary layer of the Earth. What greenhouse gases do is they absorb infrared radiation, long-wave radiation, as it's coming off the surface, and ultimately then re-radiating that back down and back out to space. The reason they're called greenhouse gases is that they work much like a greenhouse. A greenhouse is a glass enclosure where it lets in visible light from the sun and heats up during the day, but because the glass is relatively opaque to infrared radiation, to long-wave radiation, the heat stays inside even though the visible light can penetrate. And as a result, the temperature inside a greenhouse on a cold, sunny day is much, much hotter than what it would be outside. Essentially, that's what's happening with the entire atmosphere of the Earth, where the greenhouse gases essentially give you a layer, much like covering yourself with a thick comforter on a cold night. They essentially absorb infrared radiation, re-radiating it back to space and back down to the surface, but essentially increase the altitude at which the Earth is in this energy balance state where the incoming radiation is the same as the outgoing radiation. One way to think about the Earth's energy budget is to compare the Earth with our neighboring planet Venus. So Venus is about the same size as the Earth, and it's closer to the sun, so that means it gets roughly twice as much solar radiation per unit area as the Earth. So you would expect Venus to be a lot hotter, and sure enough it is. It's about 460 degrees Celsius at the surface of Venus. It's pretty steamy. But if you look at the energy budget of the two planets, one actually sees that Venus being closer to the sun is not the primary reason why Venus is so hot. The Earth gets about 340 watts per meter squared of incoming solar radiation on average around the Earth's surface, and about 100 watts per meter squared of that is reflected back to space. Most of it is from bright clouds in the Earth's atmosphere. A little bit of it is from the surface of the Earth and from especially the polar ice caps that are very white. So a little more than 2/3 of the incoming solar radiation is actually absorbed by the Earth's surface and is turned into heat and ultimately to outgoing infrared radiation. In contrast, the surface of Venus is much, much brighter than the Earth. Venus receives about 650 watts per meter squared of incoming solar radiation, but almost all of that, roughly 500 watts per meter squared, is reflected back to space because the surface of Venus is so bright. In truth, the situation with Venus is a little more complicated because it's not the surface of Venus that's so bright and reflecting the sunlight. It's actually the atmosphere itself. There's a lot of sulfate aerosols in the Venusian atmosphere. And so figuring out exactly what the albedo of Venus would have been if it had the same atmosphere of the Earth is a hypothetical question that's kind of difficult to solve. But the real point is that it's not being closer to the sun that makes Venus so hot. It's actually its ultra-greenhouse atmosphere. What that means is that if the Earth and Venus had the same atmosphere, Venus would actually be colder than the Earth, even though it's closer than the sun, because the amount of solar radiation that's actually absorbed at the planetary surface is actually much smaller than the Earth. And therefore, if it had no greenhouse gases in the atmosphere, or if it had the same amount as the Earth, it would be substantially colder. Venus's atmosphere is 100 times denser than the Earth and composed almost entirely of carbon dioxide, as well as some other trace gases that make it a very powerful greenhouse atmosphere. And that's why the surface of Venus is 460 degrees Celsius. In contrast, the atmosphere of the Earth has a very strong greenhouse effect. The total greenhouse effect is about 30 degrees Celsius. So that means that if we didn't have an atmosphere, the Earth's surface temperature would be about 30 degrees colder than it is today, but it's still mild compared to the ultra greenhouse on Venus.